I'm very glad to speak with you today. I'm going to be talking about data analysis challenges arising from plug-and-play systems. From the first industrial revolution with mechanization powered by water and steam power to the second, okay, thank you. To the second, involving mass production and assembly lines powered by the electricity, the fourth industrial revolution builds on what it started in the third with the introduction of computers and automation and enhances it with smart autonomous systems fueled by data and machine learning. Some of the popular terms that are usually used in connection with the fourth industrial revolution are Industry 4.0, that is originated in Germany, smart factory originated in Asia, and smart manufacturing that is originated in the United States. All of them represent various government initiatives with the goal to use the current advancement in technology to make factories' operations more intelligent, efficient, and responsive. So these government initiatives involve using the development of the technology to provide connectedness and real-time actionable insights on every factory floor. What differentiates specifically the U.S. Smart Manufacturing Initiative is that it emphasizes the role of the humans in the process. The human capabilities must be enhanced with technology in order for the solution to be effective on every factory floor. Unfortunately, this aspect is often being overlooked. 95% of all the factories across the U.S. are small to medium size. And all of them together contribute to 20% of the manufacturing GDP. I would like all of you to walk into a factory right now and learn more about its people and machines. This is a precision aerospace manufacturer. It has about 25 million annual revenue, employs around 50 to 60 people. It has 30 machines. It has been around 40 to 50 years, and it is family owned. There are 250,000 factories like this one across the U.S., and most of them are around here in the Midwest. If you talk to a plant manager and ask him, what are the biggest problems at your factory? He will first tell us that it's the shortage in skilled labor that they are experiencing, and he will tell us how difficult it is for them to compete with large factories for the qualified workforce. Second, he will mention thin margins that do not allow them to adopt most of the technology available right now. He will also admit that their operations are very outdated, and most likely they need to improve the operations first in order to benefit from any technology solutions. Finally, they already tried a couple of IoT solutions that did not work for them. They had some losses associated with those solutions, so they're very skeptical. If we look at the reasons why these solutions didn't work for them, the first reason is they're very costly. Some factories couldn't afford them or couldn't fully afford them. The second reason is they're very risky. For example, one factory spent $250K on a solution. After 9 months of installation, they started seeing some data, but they didn't know what to do with it. And they didn't know how to use it to solve their problems. So this solution proved very ineffective and involved a lot of losses. Another cause that the solutions are difficult to install and use. So most factories don't have experts on the factory floor. Finally, those solutions are often fragmented. And you will be surprised, and I was also surprised, but every factory has some legacy equipment. Some machines are not computerized, and some machines have old PLC logic. Most IoT solutions are not addressing those issues, so they cannot be included in a solution that results in the manual labor that the factory has to perform in order to collect the data from those machines and somehow incorporate that data to the data that is collected automatically. And it is really difficult task really difficult task for them to do that. So what we see that what they need is the vertically integrated solution from the sensor to the user interface that is easy to install and would not require any specialized expertise. One of the examples of such a solution is our Ampere plug-and-play IoT solution, where we use a sensor that is clamped on the electricity cord of the machine. As I mentioned, there are a lot of advantages of that because it is very easy to install and use, and it covers all the difficulties, so it doesn't require any expertise. Before I will show you some examples from our experience, I would like to emphasize that the principles that I am talking right now are applicable to any solution, any IoT solution that is implemented in a plug-and-play fashion, not just our solution, but of course we are talking about our experience. This is a hydraulic component manufacturer, and they have some old legacy equipment. They install IoT solution, but it could not cover that equipment. So every day, 2 hours were spent on manually collecting data from that equipment and trying to incorporate that into a full analysis in the factory. This was very ineffective. When they installed our solution, it covered the whole factory floor. They immediately were able to see and analyze the data, and they implemented some improvement projects. This is the Aerospace component manufacturer, and they actually did install some IoT solution. It took 6 months for them to install it. But even after that, they didn't see any data. Those are real examples. They didn't see any data. They were very skeptical when they plugged the sensors on the cord. They immediately started receiving the data. They saw through the software the analysis of the data. They were able to evaluate the benefits in 4 weeks and installed across the whole plant. Finally, our final example is very specific. It is interesting factory that process liquid chemicals. They need to monitor the equipment in order to comply with the regulations. They need to guarantee that the filters have a high utilization. They prefer to do it automatically, but the stoppage of this equipment is extremely costly. Any stoppage would result in semi-processed liquids immediately wasted, and they would have to clean the system and fill it with the new product. So they cannot stop the equipment. They were able to plug the sensors and start receiving the data. They could monitor the utilization of the filtering system, and now they ensure the compliance very easily. It's automated for them now. So these examples illustrate how useful it is, the plug-and-play concept in IoT solutions. But such simplicity in usage and installation leads to the challenges in the data that we are receiving from those sensors. And this leads to major data analysis challenges that I would like to talk about. First, again, I would like to note that this does not apply just to the sensor that, for example, we use in our solution, electricity sensor. In general, this could be applicable to any sensor of different type that is installed in plug-and-play fashion. The first property is most likely we will be aggregating the sum of very difficult processes that are happening inside of the equipment that we might not have a good understanding about. Second, these processes could start and stop at any time because the production of the unit could be very complex. And also there is a human operation involved in it, so we will see a very different patterns and very abrupt changes. Finally, because we don't have a control of the environment of the sensor, we have to be prepared to see much more noise than on the average system. So the data will be noisy. These unique properties, lead to some major challenges when it comes to data analysis, and namely applying machine learning to this data. Today, I would like to talk about just 3 of those challenges. And one is the lack of training data. In order for the system to be real-time and provide real-time solution, it has to be able to learn from the data. In this setting, in plug and play, it has to perform this learning process very fast. So most likely, you would have to, you could only apply a method that could learn from a very small amount of data. We have a few suggestions. Some of them are classical. For example, this problem is only solvable if you have a low number of categories. For example, on the left, you see a problem of solving a machine state. The figure is very simplified just for illustration purposes. You will see that the machine is in production. When it is green, the yellow area is machine is idle. So a machine state is an example of such problem because a machine could have 3, 4, 5 states, a very small number of states. Then you have to have access to label data because you have to perform a supervised learning. You won't have enough data to do any unsupervised learning methods. And access to label data is either you have an expert knowledge or access to expert knowledge, or you have some basic intuition. You could, like when you visually see the data, you could guess. So if these 2 criteria are hold, then you can approach and try to solve the problem. And if you are able to solve it with a low complexity model, meaning that the model will have a small number of parameters, then this model is applicable to the plug-and-play real-time setting. Yes? Yes. So we do it in real time, and this is just for simplicity. It's a very simple picture, but in reality, you saw the signals are very, you see that the signals are very different. But yes, this is what our technology does. It recognizes in real time the state of the machine. Only because of this signal. Yeah, so we are getting the signal, and machine learning algorithm perform the classification. On our side, we also recommend you, even if you have a small set of data, to do a further selection of the data. If you can come up with a measure that would signify the quality of data with respect to training, then you could apply a pre-processing learning for your data. This will result in much smaller data set, but it might improve the learning, the outcome of the model. Any questions? Okay. The second challenge is very common. It's achieving high accuracy. And there is a lot of discussion and there is a lot of misunderstanding in the community. If you are developing the algorithms in machine learning, then you know that the algorithms that are in research do not provide the accuracy needed for the applications, for example, for the industrial applications. We refer you for the good explanation to this paper that is cited on the left. But in summary, we know that the current state of the research, most of the algorithms perform with much lower accuracy than needed for us to support this technology. Moreover, most algorithms that do report a very high accuracy, in practice, they are not reproducible. Either they could not be reproduced by a different group, or the paper didn't even have enough information to reproduce that algorithm. So finally, and we do have this experience in my own, like from my own experience, I can say that those claims about high accuracy, I never saw that on our data. So finally, the measure of accuracy is a very vaguely defined topic because accuracy can be measured in one number. It's like a lot of time this is misunderstood. And so first, we recommend to choose the right measure of accuracy that works for your problem. And then once you have that, your algorithm needs to have an error correction. Error correction must be in place because it's a real time, so errors are unavoidable. You will have to have a very good error correction method that could correct your errors on the go. Finally, you would not be able to, you would have to also provide automated monitoring and retraining. Since there is so much variability in the data, you would have to perform the retraining. And this is partially why you need your method to work on a very small amount of data, because it would have to relearn the parameters and do it really fast. Finally, we would like just to give a very simple example, just to touch on the topic of recognizing changing patterns. Pattern recognition is a very popular problem in signal processing. We are only talking about one-dimensional time series pattern recognition. And if you see on the left, you might recognize this picture. It's a cardiogram, human activity measured over time. You see there are 3 nice heartbeats. It is a very clean data. Most of the research using this type of data as an input. So it is pretty simple data to analyze. On the other hand, if you would like to look at the heartbeat of the machine, what would you see? You see 4 heartbeats, right? Yeah, but you see there are some similarities, but there is a lot of difference. The signal is much more complex. So on the A plus B, you see a heartbeat of a machine, that metal cutting machine that has 2 motors that is producing the same unit 4 times. Normally, this is the data you will have from plug-and-play sensor. But for the illustration purposes, we do have a data coming from each motor. And so in A and B, you will see this data. You know that the production of the unit requires work, similar work for each motor. If you look at the highlighted, unfortunately highlighted is not, it's demonstrated, okay, great, not on the screen. Yeah, so if you look at the highlighted areas, if you look at A and B, the area that is highlighted, do you see that it is different from the other 3? It's slightly different. Yeah, it is slightly different. So the major challenge is that most methods would fail even on the better data. But so what is the cause of this change is if you look at A and B, so they're aligned in time, you see that they're very similar, all 4 of them, for each motor. But the operation on the B motor was performed with some delay, with a delay. And this could happen because of the human operator just executed some actions in a different order. So this is just for illustration purposes, and this resulted in this pattern. So essentially the same unit was produced at each time. So A plus B is the sum. A is the signal we could receive for one motor, and the B is the signal for activity on the second motor. Yeah, you will see the sum. Yeah, that's the point I'm making, but the only way how I could make it is by providing the A and B as well. Just for that, we were able to get that, but in a lot of cases, like, we cannot do it. Yeah, that was the question. Yeah, so this is how we got A and B. So the main point to take out from it is that when you plug and play sensor, it might result in a very complex data. The research hasn't been done for that. So if I am to leave you with one thought today after my talk, for industry community, we encourage you to consider designing IoT in plug-and-play fashion, because it is adaptable and useful technology, and it makes a big difference. For example, on the manufacturing, it could make a huge difference, and people could actually use your technology. For the research community, we invite you to consider to direct your research in a way that could support the development of plug-and-play technology, meaning that considering a more complex input data, assume less data for your model that you have for training. And finally, with each algorithm, develop error correction methods that could help it to achieve a high accuracy in real time. Thank you very much, and I'm happy to take any questions that you have.